doing software engineering. This is the syllabus. So we've got definition and importance of software engineering, software crisis and myths, software process framework, software development life cycle, models, waterfall model, incremental model, prototype model, spiral model, agile model. Software requirements engineering, understanding software requirements, requirement engineering process, requirements analysis, requirements modeling, DFT use case, software design principles, DFT use case modeling, software requirement specification SRS, software design and architecture, software design principles, coupling and cohesion, design pattern, refactoring architectural styles and patterns. Then we've got Unit 3, quality management, software testing fundamentals, testing techniques, white box, black box and grey box testing, unit testing, integration testing, system testing, regression testing, automated testing, tools, Selenium, JUnit, web application testing, security testing. Then we've got Unit 4, managing software projects, software project management, project planning, FPM model, software cost estimation, COCOMO model, risk management, configuration management, software maintenance, types, software maintenance, models, reverse engineering and re-engineering, change management process. So I will be referring to this book, Software Engineering, a Practitioner's Approach, but I will also take the help of AI. I will use Gemini first to cover the syllabus. Otherwise, I have been referring to this book. So let us start. I will take a screenshot. This is the prompt that I'll use. Let's see. Okay, so we've got definition. Software engineering is a systematic, disciplined and quantifiable approach to development, operation, maintenance of software. It applies engineering principles to software creation to ensure it is reliable, efficient and scalable. We've got importance, then we've got software crisis and myths, then we've got software process framework, and we've got software development life cycle, SDLC models, and I think I will just read out. First, introduction to software engineering. I read the definition, then its importance, manage complexity, cost and time control, proper planning prevents massive budget overruns and missed deadlines, quality assurance ensures the final product is secure, user-friendly and virtually bug-free. Software crisis and myth. The software crisis, the term emerged in the late 1960s when software development couldn't keep pace with rapid hardware advancements. Project frequency ran over budget, missed deadlines, were highly inefficient and delivered poor quality software that was incredibly difficult to maintain. Software myths. Misleading beliefs commonly held by managers, users, or developers. Management myths. We have a book of standards and procedures that people already know everything they need to know. Reality. These books are often outdated or ignored. Customer myth. A general statement of objectives is enough to start writing code. We can fill in the details later. Reality. Ambiguous requirements lead to project failure. Developer myth. Once we write the program and get it to run, our job is done. Reality. 60% to 80% of all effort expended on software occurs after it is delivered. Okay, so these were the software myths, software crisis, and software myth. Software process framework. A process framework establishes the foundation for a complete software engineering process by identifying a small number of framework activities applicable to all software projects. The first would be communication, heavy collaboration with stakeholders to gather requirements. Then we have got planning, then we have got modeling, then construction, and then deployment. Okay, so planning. Defining the map, risks, resources, and schedule. Modeling. Creating architectural blueprints, diagrams like UML and designs. Construction. Code generation and testing. Deployment. Delivering the software to the customer for feedback and final release. Software development life cycle, SDLC models. First is the waterfall model. Concept. A linear sequential model where development flows downward through distinct phases: requirements, design, implementation, verification, maintenance. Pros would be it is simple to understand and manage, clear milestones. And cons would be it is inflexible, changes are costly, a working version isn't seen until late in the cycle. The second would be incremental model. Concept. The project is broken down into small manageable chunks. Each increment delivers a fully functional part of the system, building upon the previous one. Pros. Generates working software quickly, easier to adapt to early feedback. Cons. Requires high-level planning and architectural design upfront. The third part would be prototype model. Concept. Developers build a simplified toy version of the software, a prototype, early on. It is given to customers for feedback, which is then used to refine the actual product requirements. Pros. Great for when the customer doesn't fully understand their own requirements, uncovers hidden needs early. Cons. Can lead to scope creep or customers expecting the throwaway prototype to be final polished product. D would be spiral model, an evolutionary model that combines the iterative nature of prototyping with the controlled systematic aspects of waterfall model. It places a massive emphasis on risk analysis in every loop. Spiral. Pros. Highly realistic for large mission critical systems where risk management is paramount. Cons. Can be expensive, requires highly specialized risk assessment expertise. E part would be agile model. Concept. Focuses on iterative development, continuous feedback, and rapid adaptation to change. Instead of rigid plans, it relies on cross-functional teams delivering working software in short cycles, sprints. Pros. Highly flexible, fast time to market, high customer satisfaction due to continuous involvement. Cons. Lack of formal emphasis on long-term design, documentation can fall apart. Okay, so Unit 2 was modeling, I guess. I don't even remember the syllabus. Okay, we will start with modeling. Okay, we will start with software requirement engineering. Requirement engineering is the process of discovering, analyzing, documenting, and maintaining a set of requirements for a computer-based system. The requirement engineering process. It isn't a one-step task. It follows a rigorous cycle. I'll just read out the text in bold ones. Inception, elicitation, elaboration, negotiation, specification, validation, and requirements management. I will start with inception. Okay, so it isn't a one-step task, it follows a rigorous cycle. Inception, establishing a basic understanding of the problem, the people who want a solution, and the nature of desired solution. Elicitation, gathering requirements from stakeholders through interviews, surveys, workshops, and focus groups. Elaboration, refining and modifying the basic requirements. This is where technical modeling begins. Negotiation, resolving conflicts where stakeholders demand competing features, high performance versus low cost. Specification, documenting the finalized requirements formally into an SRS document. Validation, reviewing the SRS to ensure it specifies exactly what the user wants with no errors or ambiguities. Requirements management, controlling and tracking changes to requirements as the project progresses. Then we've got requirements modeling. First we had the requirement engineering process. Now we've got requirement engineering. To turn raw text into something developers can build from, we use graphical and logical models. So the A part would be data flow diagram, DFD. The second one is use case modeling, and the third one is software requirement specification, SRS. These are the three ways we can turn raw text into a graphical and logical model. So let us start with data flow diagram. A DFD tracks the flow of data through an information system. It maps out where the data comes from, how it is transformed by processes, and where it is stored. Symbols, rectangles are for external entities. Circles, rounded rectangles are for processes. Parallel lines, open rectangles are for data stores, and arrows are for data flow. Then we've got levels. Level 0, context diagram, represents the entire system as a single process bubble interacting with external entities. Level 1 explodes the context diagram into major subsystem processes. Level 2 breaks down level 1 processes into microscopic details. Use case modeling. Use case modeling views the system from an end user's perspective. It describes what a system does without specifying how it does it internally. Actors, stick figures representing external entities, users, external hardware, or other software system that interacts with our software. Use cases, ovals representing specific tasks or goals the system performs for an actor. Example, login, view balance, transfer funds. Relationships, systems use associations like include, a step mandatory for the use case to complete, and extend, an optional behavior under specific conditions. Then we have got software requirement specification, SRS. The SRS is the official blueprint of the project. It acts as a legal contract and technical guide between the client, project managers, and the development team. Key attributes of a great SRS. It must be unambiguous, complete, verifiable, testable, consistent, and traceable. Software design and architecture. Once you know what to build via requirements, design tells you how to construct it structurally. Uh, so here we've got ABC, three parts under software design and architecture. Uh, A is Part A is architecture styles and patterns. Part B is fundamental design principles, coupling and cohesion, and Part C is design patterns and refactoring. So let us start with Part A, architecture styles and patterns. Software architecture acts as the structural framework of a system. Common patterns include layered and tight architecture. Components are organized into horizontal layers. Example, presentation layer, business logic layer, data access layer. Each layer only talks to the layer directly beneath it. Client-server pattern. Clean segregation where multiple clients request resources from a centralized server. Microservices. The application is split into a collection of loosely coupled, independently deployable services organized around specific business capabilities. B part is fundamental design principles, coupling and cohesion. These two metrics determine the health and maintainability of your software code. Cohesion. Aim for high cohesion. Measures how closely focused the responsibilities of a single module are. A highly cohesive module does one thing and one thing only. Example, a function that only calculates taxes. Coupling. Aim for low loose coupling. Measures the degree of interdependence between different modules. If changing code in module A breaks module B, they are tightly coupled. We want modules to be independent so that updates don't cause a domino effect of bugs. Design patterns and refactoring. Design patterns. Reusable time-tested solutions to commonly occurring software design problems. Example, singleton pattern to ensure a class only has one instance or observer pattern for event handling. Refactoring. The process of changing a software system in such a way that it does not alter the external behavior of the code, yet improves its internal structure, cleaning up the smelly code to reduce technical debt. So we are moving on to Unit 3, Quality Management. Okay. This unit is all about verifying the software we planned in Unit 1 and designed in Unit 2 actually works correctly, securely and efficiently. So Unit 3 is Quality Management. I'll read out the headings first. Software testing fundamentals, testing techniques, and levels of testing, specialized testing domains. It has got 4 subtopics. Then under software testing fundamentals, we've got verification versus validation. Under testing techniques, we've got white box testing, black box testing, and gray box testing. And under levels of testing, we have got unit testing, integration testing, system testing, regression testing. And under specialized testing domains, we've got web application testing, security testing, automated testing tools. And under automated testing tools, we have got Selenium and JUnit. So let us read the third unit. We will start with software testing fundamentals. Testing is the process of executing a program with the explicit intent of finding errors. It provides a quality check to ensure the software matches requirements and don't crash in production. Verification versus validation. Verification. Are we building the product right? Evaluates, documents, plans and code without running it. Validation. Are we building the right product? The actual execution of the software to see if it functions as expected by the user. So this was the difference between verification and validation. So verification occurs before the actual execution, and validation occurs after the execution of the software. Alright, so next we have got testing techniques. Part E is white box testing, structural testing. Testers look inside the system. They have full access to the source code, internal structure and design. First is focus, checking code paths, loops and branches and statements for logical gaps or dead code. Then we've got black box testing. Then we've got techniques, basis path testing, control structure testing. Now we've got black box testing. Testers treat the software as an opaque black box. They do not look at the internal code structure. They only examine the inputs and outputs based on software specification. Focus, ensuring the system does what it's supposed to do from an end user perspective. Techniques, equivalence partitioning, grouping valid invalid inputs together, boundary value analysis, testing system limits like checking values just below, at or above a maximum threshold. Gray box testing, a hybrid approach. The tester has partial knowledge of the internal data structure and algorithms, which helps them design more efficient, effective functional tests without needing full access to the source code. Now we've got levels of testing. Testing is executed progressively, moving from small pieces of code to entire system. Let us look at this. It has got unit testing, integration testing, system testing, and regression testing. We will start with unit testing. Testing individual components, modules, or functions in isolation, typically handled by developers using tools like JUnit. Integration testing, combining individual modules together and testing them as a group to ensure they communicate and transfer data correctly. System testing, testing the fully integrated, complete software package as a whole to evaluate its compliance with specified requirements. Regression testing, rerunning previously functional test cases after code changes, patches, or updates have been made. This ensures that new modifications haven't introduced fresh bugs into old, stable code. Then we've got specialized testing domains. The first is web application testing, evaluating a web application's functionality, usability, compatibility across different browsers and performance under variable loads. And then we've got security testing, uncovering vulnerabilities, flaws, or risks in the software to prevent malicious attacks, data breaches, and unauthorized access. Then we've got automated testing tools, using specialized software tools to execute tests automatically, log results, and compare outcomes with predicted targets. Selenium, a widely used open source framework for automating web browsers. JUnit, a targeted unit testing framework for Java programming languages. Yes, we can start with Unit 4, I guess. This final unit focuses on the managerial side of software engineering, how to plan budgets, estimate efforts, manage risks, and maintain the software long after it has been deployed. Unit 4, Managing Software Projects. Software Project Management, SPM. Project management involves planning, monitoring, and controlling software projects to ensure they are delivered on time, within budget, and up to quality standards. Project planning. I'll read out the topics first. Project planning, cost and effort estimation models, risk and configuration management, software maintenance type, software maintenance and evolution, change management. It has got 3 topics and subtopics of. There's no subtopic for A. There's subtopics for cost and effort estimation models, FPA model, function point analysis, and COCOMO model, constructive cost model. Then we've got risk and configuration management. The first part is risk management, identifying, analyzing, and mitigating potential problems before they can derail a project. The second one is configuration management, SCM, tracking. And for software maintenance and evolution, we've got A, B, and C parts. We've got software maintenance types, which are corrective maintenance, adaptive maintenance, perfective maintenance, and preventive maintenance. And for B part, we have got reverse engineering, the process of analyzing a software system to identify its components and interrelationships, creating representations of the system at a higher level of abstraction. Essentially, you take an existing product and deduce how it was designed without looking at the original blueprint. Okay, and we've got re-engineering, the examination and alteration of a system to reconstitute in its new form. Reconstitute it in a new form, it involves a combination of reverse engineering, code restructuring, and forward engineering to modernize legacy system. Then C part is change management process. Okay. So the first one was software project management, SPM. Project management involves planning, monitoring, and controlling software projects to ensure they are delivered on time, within budget, and up to quality standard. Project planning, the initial phase where project goals, scope, constraints, and milestones are defined. It creates the roadmap that guides the engineering team through SDLC. B. Cost and effort estimation models. Before writing code, managers must estimate how many developers are needed and how much the project will cost. Two primary models used are FPA model, function point analysis, a sizing technique that measures the functional size of software from the user's perspective. It counts out inputs, outputs, inquiries, internal files, and external interfaces to calculate function point independent of the programming language used. Then we've got COCOMO model, a procedural estimation model that uses a mathematical formula to predict project effort and duration based on the size of the software, measured in KLOC, kilo lines of code. It operates across 3 levels: basic, intermediate, and detail, and classifies project into 3 modes. Organic, small, stable teams building familiar software. Second is semi-detached, medium-sized teams with mixed experience levels working on remotely complex systems. Then we've got embedded, projects with tight hardware, software constraints, and strict regulations. Example, air traffic control systems. Next we've got risk and configuration management. The first part is risk management, identifying, analyzing, and mitigating potential problems before they can derail a project. The process, reactive or proactive risk strategy involving risk identification, what could go wrong, risk projection analysis, how likely is it and how bad it will be, and risk mitigation, monitoring, and management. RMM. How do we prevent it if it happens? Then we've got configuration management SCM, a tracking and control activity that manages changes made to software artifacts, code, documentation, models, test cases over time. Purpose: SCM ensures that developers don't override each other's work and allows team to uh, roll back to a stable version if a new update breaks the system, using tools like Git. Software maintenance and evolution. Software does not stop changing once it is delivered. In fact, a majority of software costs go into maintenance. A. Software maintenance types. There are four primary reasons to modify software after delivery: corrective maintenance, fixing bugs, crashes, or logical errors discovered by user in production. Second is adaptive maintenance, modifying the software to keep it operational in changing environment. And the third one is preventive maintenance, uh, modifying code to prevent future bugs, improve code readability, or simplify future maintenance tasks, often tied to refactoring. Then the B part is reverse engineering and re-engineering. I think we went through this part. Then the C part is change management process, a formal workflow used to ensure that any requested changes to the software project are properly reviewed, approved, tested, and documented before being implemented. This prevents unmanaged changes, scope creep from destabilizing the code base. Alright, so I think I have covered the syllabus, although I'm not confident about it, but still I remember something which is better than nothing. So I think I'll end it here.